Hey guys, this is Elaine, and in this video I'm going to talk about radioactivity. I divide this topic in two parts, and this is part 2. If you have not watched part 1, the link is going to show right here, and it will help you to have a better understanding about this topic. So let's start by remembering radioactivity, what means and the emissions that will happen with radioactivity. So when we talk about radioactivity, we are talking about radioactive decay. The illustration here shows the nucleus of an atom, and inside the nucleus we have protons and neutrons. And remember, certain combinations of protons and neutrons will either make the nucleus stable or not. If the nucleus is not stable, there is an excess of energy there which needs to be released, either in the form of electromagnetic wave, gamma ray, or particles, alpha particles, beta particles. Alpha and beta particles are made of particles that comes from the nucleus. That means every time they are emitted, there is a change in the number of protons here inside the nucleus. That means there is a change in the atomic number of that nucleus. And when that happens, we have a different element. As the unstable nucleus attempts to become stable, it emits radiation and changes into a different element as the number of protons changes. So this summarizes what I just said. This process is called radioactive decay, and it continues until the forces in the nucleus are balanced and stable. What is activity? It is impossible to predict exactly when a particular nucleus will decay. However, the probability per unit time that a given nucleus will decay is constant. The activity of radioactive source is the number of decays per second from the unstable nuclei present in the source. The SI unit of activity is becquerel. A source that emits 1 particle per second has an activity of 1 becquerel. So 1 becquerel equals 1 disintegration per second. Another unit for activity is the Curie. 1 Curie equals 3.7 10 to the 10th becquerel. Half-life. Each radioactive element decays at a unique rate. This rate is known as half-life. So each element will have a different half-life. So half-life is the amount of time it takes for approximately half of the radioactive atoms in a sample to decay into a more stable form. That means after 1 half-life, we are going to have 50% of the initial activity in that sample. So let's do this example here. We have iridium-192 again, just because we use this in radiation therapy. The half-life of iridium-192 is approximately 74 days. And for this example, the initial activity of this sample is 10 Curie. So let's think about this. After 1 half-life, that means 1 times 74 days, which will be equal to 74 days. So after 1 half-life, we will have 5 Curie, which is exactly 50% of the initial activity. After 2 half-lives, 2 times 74 equals to 148 days. So after 148 days, we are going to have 2.5 Curie, which is half of the previous one. And that goes on. The source activity is considered insignificant after 10 half-lives. This equation here relates the initial activity, half-life, and time. With this equation, we can calculate the activity of a sample of a source at any time. We just need to have the initial activity and the half-life. So T is the time, AT is the activity at time T, A0 is the initial activity, and T half is half-life. So let's do this simple math here. Iridium-192 source has initial activity of 10 curie. What is the source activity after 222 days? So let's see what we have here in this problem. What's given in the problem is the initial activity, 10 curie, 10 curie. What we know there is an iridium-192 source. That means the half-life is 74 days, approximately. So we plug those values into that equation. 10 here for initial activity, 74 for the half-life. And what we need to calculate? We need to know what is the source activity after 222 days. So T equals 222. Let's calculate the activity at that time T. We plug all the values we have in the equation, initial activity, half-life, time T. So it will be 10 times E to the negative ln of 2 times 222 days divided by 74 days. That equals to 1.25 curie. So the activity of the source after 222 days is 1.25 curie. So that's what I said. We can, with this equation here, I go back. With this equation here, we can calculate the activity of a sample of a source at any time. We just need to know some parameters like half-life, initial activity, and the time that we are looking for. So those are the sources I used for this presentation. There was also a link under each picture. So here it ends part 2. Again, if you have not watched part 1, the link will show right here. It will help you to have a better understanding about this topic. So this is it guys. See you in the next video. Thanks for watching.